Welcome everyone, it's a pleasure to present to you today. My name is Alejandro Lara and I work at the Faculty of Architecture, Building and Planning at the Melbourne School of Design of the University of Melbourne. Today I will present to you a work that was done in conjunction with Dr. André Stefan, who's a professor at the Université Catholique de Louvain, and Dr. Robert Crawford, who's a professor at the University of Melbourne. Our work is a comparative study that looks at the environmental performance of an upcoming development here in Melbourne, focusing on the effect of the data used to conduct a life cycle assessment, which is called a life cycle inventory. The majority of existing studies on the life cycle assessment of buildings use a bottom-up approach called process analysis, which can significantly underestimate embodied energy and emissions. In order to ensure a more comprehensive coverage of these flows, process data can be augmented with top-down macroeconomic data, which is known as input-output data. The resulting hybrid life cycle inventory provides embodied energy and greenhouse gas emissions figures that cover the entire supply of material chains. Recently, a group of researchers led by Dr. Robert Crawford at the University of Melbourne produced the EPIC database of embodied environmental flow coefficients for construction materials in Australia. This comprehensive database uses the same method as the former database of Crawford and Treloar, released in 2010, which is based on 1997 input-output data and process data from the 1990s to produce hybrid coefficients. This offers a unique opportunity to compare the previous and new databases of hybrid coefficients as applied to a case study development in order to understand the changes in the data and their implications on decision-making. The scope of our work is limited to the initial and recurrent embodied energy and greenhouse gas emissions of an upcoming housing development in Melbourne. The system boundaries account for life cycle embodied energy and life cycle embodied greenhouse gas emissions, which are defined as the sum of primary energy and greenhouse gas emissions associated with the construction process, including construction materials and associated transportation, administration, and other services, including the recurrent embodied energy and greenhouse gas emissions related to the replacement of the materials. These are equivalent to stages A1 to A5 and B4 in the European standard. Our period of analysis is 50 years. Here's an overview of our research design. The first step is related to the modeling of the case study. We used the software Energy Metric, which was developed by Dr. André Stefan in 2013, and this software enables to quantify the embodied energy and greenhouse gas emissions of buildings and neighborhoods. It allows and enables the specification of dimensions of each building, estimating bills of material quantities, and the initial and recurrent embodied environmental flows over a specified period of analysis. We relied on two versions of the hybrid embodied and greenhouse gas emissions coefficients, the 2010 Crawford and Treloar database and the EPIC database from 2019, which I previously discussed. And we use the same software and assumptions for the quantification of environmental flows to enable a more robust comparison. The second step relates to computing the life cycle embodied environmental flows and producing a comparison. This was also done on Energy Metric. The quantities of materials within each building within the development are multiplied by the relevant hybrid embodied flow coefficient, and also by a wastage coefficient that accounts for on-site waste. A so-called input-output remainder is added to the total to account for non-material inputs along the supply chain of the building. For our case study, we chose a new housing development located in Melbourne, Australia. This development is characterized by its strong agenda on improved environmental performance, notably through a reduction in materiality to reduce embodied flows. The development is called the Nightingale Village and is expected to be finalized in 2021. It will deliver approximately 185 dwellings and integrated services within 6 mixed-use multi-story buildings, spanning over approximately 14,000 square meters of gross floor area. Green environmental credentials are claimed following a comprehensive sustainability strategy that touches on the embodied, operational, and transport phases of the life cycle, a minimum 7.5 nationwide energy rating scheme, the Nathers rating, and an average 80% built environment sustainability scorecard rating. So that's the best rating across all the buildings. The materials and constructions assemblies are informed by the architectural plans and material schedules included in the planning application documentation, advertised by our council to ensure the broadest possible representativeness of the development. In this table, you can see a summary of our results. The life cycle embodied energy of the case study development decreased by 17.6%, and the greenhouse gas emissions decreased by 5.1%. This is when using the 2019 EPIC database compared to the older database. It's important to note the significant initial embodied environmental flows associated to this case study, mainly due to the choice of more energy-intensive and emissions-intensive materials with a longer lifespan. So this translates to the initial requirements. The extent of difference in the embodied environmental flow intensities of individual materials between both 1997 and 2019 data varies broadly, as you can tell from these two charts here. For instance, the embodied energy and emissions of paint did not change significantly. It increased 3.8 and 5.1% respectively, while the embodied energy and emissions of sand and stone rose dramatically, increasing by 5,622% and 7,280% respectively. For glass, the embodied energy and embodied emissions dropped by around 80%. And these changes are in part due to the much higher resolution in the process data of the 2019 database, which jumped up to 4,500 processes approximately, compared to the few hundred processes available in the older version. In terms of the ranking of the top 5 contributors to both lifecycle energy and greenhouse gas emissions, these changed. Using 1997 data, steel, glass, other finishes, concrete, and aluminum were the top 5 contributors. And with the 2019 data, this ranking shifts to aluminum, steel, concrete, paint, and insulation for embodied energy, and to concrete, aluminum, steel, paint, and insulation for embodied greenhouse gas emissions. In terms of assemblies, there is a significant reduction in both embodied energy and greenhouse gas emissions, ranging from 15 to 98%. The most notable decrease is in the embodied energy and emissions of photovoltaic panels, both in absolute and relative terms. And also some assemblies such as finishes and flooring, which are ceramic tiles, witnessed an increase in their embodied energy and greenhouse gas emissions. In terms of the top 5 contributors, in terms of assemblies, this remained the same, except for other finishes replacing photovoltaic panels. And this is due to the respective increase and drop. And also very importantly, but not shown in these charts, are the non-material inputs across the supply chain. These changed, increasing 42.6% for embodied energy and 48% increase in terms of greenhouse gas emissions when using the new data. And these were not plotted on this graph since they're not associated with a particular material or assembly, but they're extremely significant and represent more embodied energy and emissions than any other assembly category. This increase is mainly due to the fact that the overall energy and emissions intensities of the residential building construction sector have remained similar, while the price of construction per square meter has increased following the base of inflation rate. To summarize, our results show an overall decrease in life cycle embodied energy and greenhouse gas emissions when using more recent data. And this is due firstly because of an overall increase in the energy efficiency of industrial processes over the last 2 decades. And this is translated into reduced embodied energy and greenhouse gas emissions. Also, the 2019 data integrates significantly more detailed process data compared to the 1997 data, which reflect far more accurately the relevant industrial processes of specific materials. Despite the significant changes in embodied energy and greenhouse gas emissions, the ranking of assembly types is not significantly affected, meaning that the areas of focus to reduce embodied energy and greenhouse gas emissions remain fairly similar, essentially reducing glazed surfaces, removing unnecessary partitions, reducing the amount of finishes where possible, and carefully choosing structural materials. However, when looking at particular materials, the new data shows significant changes to embodied energy and greenhouse gas emissions intensities. And finally, we found the proportion of process to input-output data for specific materials can have a considerable effect on its hybrid coefficients. Altogether, this study shows that access to comprehensive and reliable data has improved over recent decades. However, users should continue to be cautious when relying on this and similar data to make design decisions. If you have any other questions, please do not hesitate to reach out to myself or my colleagues, and thank you very much for your time.